I'm looking at a question about understanding partial dependence plots, which are created using a scikit-learn tool called PartialDependenceDisplay. The question tests your understanding of how to interpret these plots to understand how features affect a model's predictions. This refers to a specific function within the popular Python machine learning library, scikit-learn, that's used to create partial dependence plots. I use this function to visualize the relationship between features and the target variable. This is the type of model used to make predictions. A gradient boosting regressor is a powerful machine learning algorithm that combines many simpler models to make very accurate predictions. I need to understand this to see the PDP. I'll be interpreting a partial dependence plot. PDPs show how changing a single feature affects the model's predictions, holding other features constant on average. It helps me understand feature importance and potential interactions between features. These are the two input features whose effect on the target variable I am investigating using the PDP. These features are analyzed to determine how they influence the model predictions. This statement is analyzing whether increasing feature underscore always increases the prediction. I will check if this is true from the PDP. This statement explores the idea of interaction effects. I'll examine if the plot suggests the effect of one feature changes depending on the value of the other. This statement is about the suitability of a linear model, which assumes a straight line relationship. I'm looking to see if the nonlinear nature of feature underscore b on the PDP is a problem for linear modeling. This statement is about definitively proving the importance of the features. I will check if the plot can definitively state that feature b is less important than feature a. This instruction tells me that I need to select all the correct statements from the provided options. I'm interpreting a partial dependence plot, which shows how a single feature affects the prediction, while ignoring other features' effects. Think of it like isolating one variable to see its impact. I'm presented with a question about interpreting a partial dependence plot, PDP, generated by scikit-learn's _PartialDependenceDisplay. The PDP visualizes the relationship between two features and the target variable from a gradient boosting regression model. I see a non-monotonic relationship for feature underscore b, meaning the relationship isn't simply increasing or decreasing. A linear model assumes a straight line relationship, so it wouldn't capture the ups and downs. A curvy line, non-monotonic, indicates that a linear model, which assumes a straight line, simply won't work well. That makes option C true. Even though feature underscore a looks simple and strong in the plot, that doesn't automatically mean feature underscore b is less important. The PDP only shows the average effect. There might be complex, hidden interactions with other features. Therefore, I cannot make that definitive statement about importance, so option D is false. The complex relationship for feature underscore b suggests that its effect on the target might depend on the value of feature underscore a. This is a hint of an interaction effect between the features, making option B true. I've analyzed all the statements and made my determination about the accuracy of each. I'm ready to move on. This question tests my understanding of how to interpret a partial dependence plot, PDP, a visualization tool used to show how a single feature affects a model's predictions after accounting for other features. I need to use my knowledge of PDPs to interpret the relationship shown between two features and the model's target variable. It's like detective work, but instead of clues, I have a chart. Let's solve this mystery. A non-monotonic relationship means the relationship between feature B and the target variable isn't consistently increasing or decreasing. It goes up and down, and that's important to see. A linear model assumes a straight line relationship, so if I see this kind of curve, I know that a linear model isn't going to capture the pattern very well. Think of trying to fit a straight line through a roller coaster track. It just won't work. I can't definitively say feature B is less important based only on this PDP. While the plot might suggest feature A has a simpler and seemingly stronger relationship with the target, feature B could still be important. Its complex relationship might hide a significant influence. A simpler visual doesn't necessarily equal less importance. It is like assuming someone's quieter than another, making them less influential. It's important to remember that PDPs show marginal effects, and they don't always capture the whole picture. I need more information. The complex relationship for feature B suggests there's more to the story. It might be interacting with feature A, meaning the impact of feature B on the target depends on the value of feature A. It's like a recipe. The effect of one ingredient might depend on another. This needs more investigation. This is about understanding what a partial dependence plot, PDP, shows me. It helps visualize how a particular feature affects a prediction, averaging out the influence of other features. It helps me see important things about my model, but I need to be cautious about what it tells me and what it doesn't. Think of it as one piece of a larger puzzle. I see this as the core concept. We're looking at a partial dependence plot, or PDP for short. A PDP visually shows how a single feature influences a model's prediction, ignoring other features' effects. Think of it like isolating one variable to see its impact. The question tests my understanding of PDPs. I need to analyze a plot showing how feature_A and feature_B relate to the target variable. I will figure out how a change in each feature impacts the target variable. This statement suggests that the effect of feature_A on the target might change depending on the value of feature_B, and vice versa. This is called an interaction effect, and it's something I definitely need to look for when analyzing the PDP. This statement is about how well different models fit my data. A linear model assumes a straight line relationship. If feature_B has a complex, non-monotonic relationship with the target, meaning not always increasing or decreasing, then a linear model would be a bad choice. To capture that complexity, it wouldn't properly fit the data. This statement deals with feature importance. I need to consider that while feature_A might look more important in a simple sense, based on the PDP alone I cannot definitely say feature_B is less important. Feature_B could have a complex relationship with the target, even if its direct effect isn't as straightforward as feature_A. This statement says that whenever feature_A increases, the target variable will always increase too. But a PDP averages out the effect of other features. The relationship might not always hold true, especially if feature_A and feature_B interact. It's a simplification, and might not be completely accurate. This is just a reminder we're dealing with visual information, the actual PDP graph. I need to interpret what I see there to answer the question correctly. I'm analyzing a partial dependence plot, PDP, to understand how two features, feature_A and feature_B, affect a target variable. The plot shows feature_A has a clear positive relationship with the target, meaning as feature_A increases, so does the predicted target value. However, feature_B shows a more complex, nonlinear relationship. It goes up and down, not following a simple pattern. This question tests my understanding of what this plot means. This is the instruction for this multiple choice question. I need to pick all the correct statements about the PDP I just described. I see a complex relationship for feature_B, and this could mean that how feature_B affects the target depends on the value of feature_A. That's an interaction effect. It needs more investigation to be sure. The unpredictable, wavy line for feature_B shows that a simple straight line, which is what a linear model assumes, won't capture its relationship to the target variable well. A nonlinear relationship needs a nonlinear model. While the plot shows a generally positive relationship between feature_A and the target, it doesn't mean that this is always true, regardless of feature_B. The PDP averages out the effects of feature_B, but an interaction could still exist. Just because feature_A has a simpler relationship in the PDP doesn't automatically mean feature_B is less important. It might still be really influential, even if it has a more complex relationship. The PDP only shows a simplified view, and we need more advanced techniques to truly compare feature importance. This question tests my understanding of partial dependence plots, PDPs, specifically how I interpret them when using the scikit-learn libraries PartialDependenceDisplay function. I need to analyze a PDP for a gradient boosting regressor model and determine which statements accurately reflect the plot's implications. It's all about applying my knowledge of PDPs to a practical scenario. I'm given a scenario where a trained gradient boosting regressor model is used to create a partial dependence plot. The plot reveals a clear positive relationship between feature A and the target variable. As feature A increases, so does the predicted target value. However, the relationship between feature B and the target variable is more complicated. It's non-monotonic, meaning it doesn't consistently increase or decrease. This immediately suggests that the relationship is not linear. This statement is too strong. While the PDP shows a positive relationship between feature A and the target variable, I need to remember that PDPs average over other features. The relationship may not hold true for all values of feature B because of potential interactions between features. Therefore, I can't assume this statement is always true. This statement is likely true. The non-monotonic relationship for feature B hints at a possible interaction with feature A. The effect of feature B on the target variable may be influenced by the value of feature A. It requires more investigation, but it's a strong possibility. This is likely true. The non-monotonic relationship shown in the PDP for feature B clearly indicates a nonlinear relationship. A linear model would not be appropriate here because it assumes linear relationships between features and the target variable. The model would fail to capture the complexity observed in the data. I cannot definitively conclude this from the PDP alone. The PDP shows the marginal effect of each feature, averaging over other features. Feature B might have significant influence through interactions, even if its simple marginal effect seems less pronounced than feature A's. Provided options evaluate my understanding of PDPs. I have to assess the statement's validity considering the nuances of PDPs, including the averaging effect and the possibility of interaction effects between features. I need to focus on what information the PDP actually provides. It's not about memorization, it's about using my understanding of PDPs to reason about the given scenario. This is the instruction for answering the quiz question. It's about identifying all the statements that are correct based on my analysis of the partial dependence plot. This is the general topic of the question. I need to understand what a partial dependence plot, PDP, is and how to interpret it.